Good morning, everyone, and thank you for coming to my talk. My name is Bob Steagall, and they tell me I'm a software architect with Finch Computing. I began using C++ in 1992 when I was a young research assistant working for the departments of physics and radiology at university hospitals in Cleveland. And I can tell you from personal experience that the evolution of the language and its libraries since then, especially over the last 7 or 8 years, is truly astounding. With the rapid uptake of C++ 11 and now 14, it's hard to imagine that there ever was a time before R-value references and lambdas and variadic templates and soon concepts and things like this. As you can see, this talk was initially entitled Lightweight Object Persistence with Modern C++. However, as always happens when I complete something for a deadline, after the deadline passes, I begin to obsess over the many ways it could have been made better. So in the interest of improved precision, for today I've amended the title to be Lightweight Object Persistence with Relocatable Heaps in modern C++. I'm not sure that it's much of an improvement, but at least my good intentions are captured in the video record now. Before we dig into the content, I have a request and a couple of notes. First, there's a fair bit of material to get through, and so I ask that you please hold your questions until the end. Each slide is numbered in the lower right-hand corner, so if you have a question, please take note of that slide's number, and we'll go back to it. Next, like our esteemed 43rd president, I may make up some words along the way. Hopefully their meaning will be clear from the context. Also, I'm going to use the word concepts throughout this talk, and when I do, I mean concepts with a lowercase c, not the new language facility. I'd like to begin describing what this talk is about. I submitted the abstract for the talk because I wanted to share some results of some work that I've been doing off and on for the last few years. So first, I'd like to describe a way of thinking about allocator design that may be helpful when you design your allocators. I decompose the problem into a small number of concepts which could be implemented as policy types that make designing high-performance allocators a little easier, or at least they did for me. And for my money, this decomposition, or mental framework, if you will, is the most important thing to take away from the talk. Secondly, I'd like to outline one solution to the problem of object persistence, a solution that may be useful in certain cases. Now, there's no sexy metaprogramming or slick concurrency techniques. Instead, just a straightforward way of implementing one small form of object persistence. For another solution along the same lines as mine, and one that is very mature, I recommend that you look at boost inner process. Now, although we're going to construct a standard conforming allocator along the way, this talk is not a tutorial on allocators. There are plenty of books and articles and online references that describe the details of allocators and how to build them. This is also not a proposal for how to improve the standard allocator facilities. There have been countless electrons sacrificed on this altar over the last few years. Andrei Alexandrescu has been very vocal in this area and gave a great talk on the topic last year at this very conference, and I recommend you check it out on YouTube. He's given similar talks in the past, and parenthetically, the only quibble I have with Andrei's point of view is that I think he doesn't go quite far enough. I hope to move that ball a little bit further down the field today. Finally, this talk will not provide a complete off-the-shelf framework for object persistence. Writing allocators and implementing object persistence is difficult and challenging work, and I do not have the one true library that will solve all of your persistence problems. You're going to need to figure out the best way to do that for yourself. So the first half of the talk will be a discussion of some concepts. Then I'll show some code, and finally I'll hopefully provide a demo that may or may not work. So let's begin in the context of a particular problem. In my case, at my current and previous employers, critical business operations depend on proprietary in-memory databases that are written in C++. Although these databases are very different in the design and the content they hold, both databases store lots of complex data with non-trivial relationships among the data. So if I step back and generalize the problem, I have a set of types. These types have container data members. The elements of those containers may themselves also have container data members. So I could have a nested hierarchy of containment. I have a large number of these objects in memory, usually more than 10 gigabytes, and quite often substantially more than 10 gigabytes. The objects of these types typically have time-consuming construction or copy or traversal operations. And so, naturally, I want to be able to take this data and save it to persistent storage so I can recall it later and use it, or transmit it across the wire so somebody else can use it. Of course, the question is how to accomplish these feats. Well, it goes without saying that we can turn to serialization. Wikipedia has a nice definition: the process of translating data structures or object state into a format that can be stored in a file or temporary buffer, or transmitted across a network connection and reconstructed later in the same or other computer environment. In many cases, this is a two-step process, as we all know. Step one, we iterate over and serialize the source objects into some intermediate format. For example, JSON, which all the kids love these days, or YAML, or XML, or protocol buffers, or a proprietary format, etc., etc. Now, this iteration could be recursive, it could be level order, it could be something else. But whatever it is, it has to be prearranged with or discoverable by the entity on the destination side that's doing the deserialization. Now, of course, the obvious purpose of serialization is to save important object state. Step two is to deserialize the intermediate format into destination objects. And here, the obvious purpose is to recover important object state. If we've done this properly, the result will be that on the destination side, each destination object will be semantically identical to its corresponding source object. I'm not going to define semantically identical, but I think we all have a pretty good idea what that means. Now, when we talk about serialization in this context, this is what I think of as traversal-based serialization. Traversal because sequences of objects and object containment hierarchies must be traversed in order to perform the serialization of each object. So let's talk briefly in very general terms about the intermediate format, because I think there are some useful ideas here. First, whether implicitly or explicitly, the intermediate format describes a schema. And here I'm using the word schema in a very loose sense to mean the relationship between an object and other objects. For purposes of serialization, I think of two kinds of relationships: containment and reference. And usually it's the representation of a reference relationship that poses the tough problems. Secondly, the intermediate format provides or can provide several forms of independence of three varieties. The first is architectural independence. And here, I think of independence from issues of things like byte ordering, class member layout, or address space layout. And here, think of serializing objects that exist on an Intel-based architecture and deserializing them on a Power architecture or a Spark architecture. The second form of independence that I think of is what I call representational independence. For example, I might have a list of vector of char on the source side, which when deserialized on the destination side becomes a list of string. One could argue that those objects are similar enough that we've done the persistence correctly. This is an example of something I think of as being intra-language representational independence. And on the other side of that coin, I might have a list of string in Java, which after wandering through the desert of JSON becomes a list of string in C++. And here I think of this as being inter-language representational independence. The final concept is that of positional independence. And what I mean by this is that the intermediate format can provide independence such that when a destination object is deserialized in a destination process, its important state is preserved even if the destination object exists at a different address in the destination process. And this is actually sort of the key concept here behind the rest of the talk. We all know from experience that there are costs and risks associated with this approach. We don't yet have standardized mechanisms for compile time or runtime reflection in C++. So at the end of the day, code has to be written or generated or both. And the code has to traverse the source objects on the source side and render them into some intermediate format. And on the destination side, the code has to parse the intermediate format and reconstruct the destination objects. I think most of us know that code like this can rapidly become complex and fragile. There's an engineering cost associated with these activities, and it can be non-trivial in real-world systems. There's a temporal cost associated with traversal-based serialization. By its very definition, serialization is linear, and therefore, in general, the entire stream must be read sequentially, which typically precludes any sort of parallelism. This can be an expensive proposition if your object construction is time-consuming on the destination side. Likewise, there's a spatial cost. Many common intermediate formats are verbose. XML, for example, is the poster child of excessively verbose data interchange formats. There are risks associated with traversal-based serialization. Our intermediate format may allow private implementation details to be exposed, details that we would like to keep private. So the risk from this is that on the destination side, encapsulation might be violated when destination objects are reconstructed, and this may in turn break class invariance or violate constraints that we expect to hold between objects on the destination side. So to sum up everything there is to know about traversal-based serialization in one slide, it's as close as we can come to a universal technique for implementing object persistence. If you're willing to put in the effort, you can find a way to make it work for you. On the other hand, it can be expensive to implement and maintain, and you generally have to be very careful to keep your code from becoming overly complex or stale or fragile. So, given these circumstances, is there a way for me to avoid all the hard work involved with traversal-based serialization? In other words, can I pull a Kobayashi Maru and change the parameters of the problem to make my life easier? Well, let's change the problem statement. Suppose that I don't need architectural or representational independence. Suppose that my source and destination platforms are the same or very close. Suppose that I'm positive the class layouts and corresponding source and destination objects are going to be exactly the same. And suppose I'm willing to use the same object code on either side, or code that's very close. If I make these assumptions, can I now implement a form of object persistence that does not require any sort of per-type serialization or deserialization code that allows me to persist standard containers and strings and be able to use standard algorithms on the destination objects after deserialization, and that uses fast binary I/O like write and read or send and receive? Clearly, we can do some of these things now. I can save an array of PODs to disk or send it over the wire, and if I'm careful about what I put in it and how I interpret it, everything will work just fine. But I want to work at a slightly higher level than plain old data structures. So here's an idea. How about a relocatable heap? I usually think of the heap as being a magic black box. I ask it for some memory, and if the planets are aligned and the gods are willing, a small window into that box opens, revealing a chunk of memory that I can use for a while. When I'm done with that memory, I hand it back to the box and the window closes. Well, wouldn't it be cool if I could pick up that black box and save it to disk so I can restore it later, or share it with another process, or send it across the wire to somebody else? In other words, wouldn't it be cool if I could relocate the heap? So by fiat, I'm going to declare that a heap is relocatable if it can be serialized and deserialized with simple binary I/O, and after deserialization at a different address in the destination process on the destination machine, the heap itself continues to function correctly, and the heap's contents continue to function correctly. In other words, after relocation, all class invariants are preserved for the heap and all the destination objects it contains, and all the destination objects are semantically identical to their corresponding source objects. As experienced C++ programmers, we all know intuitively that for a silly scheme like this to work, there must be some restrictions on the types that can be used by and stored within such a relocatable heap. And there are. Every object in a relocatable heap must be of a relocatable type. And by in the heap, I mean the objects used to implement the heap itself, as well as the heap's contents. So this begs the question of what is a relocatable type? And again, by fiat, I will declare that a type is relocatable if it can be serialized by writing raw bytes, for example, by being the source argument of a write or mcopy operation, and it is deserializable by reading raw bytes, for example, being the target arguments in a read or memcopy operation, and A destination object of that type is semantically identical to its corresponding source object, regardless of the destination object's address in the destination process. So what kind of types are relocatable? Well, it's pretty straightforward. Integer types and floating point types. Also, POD types, which, when unwrapped, ultimately contain only integer and floating point types. Everything else is not relocatable. Well, let's look at a few cases. Ordinary pointers to data are not relocatable because the data to which they refer on the destination, in the destination process may exist at a different address than in the source process. Pointers to member functions, static member functions, and free functions are not relocatable because the object code to which they refer is very likely going to exist at a different address in the destination process. Likewise with types that have virtual functions. This is because their vtables will very likely exist at a different address in the destination process. And finally, types or values of types that express some sort of process dependence are not relocatable. And here I'm thinking of things like file descriptors or Windows handles. Of course, by definition, process-dependent handle types are meaningless outside their own process. Now, these might seem like pretty severe restrictions, and they are, but if you think about them, they sort of specify the kind of data that one might keep in a record residing in a table in an in-memory database. In other words, the kind of stuff that I do day to day. So let's sketch out a design for this. First of all, a relocatable heap would need to provide methods to initialize and serialize and deserialize the heap. It would also need to provide methods to store and access something I call a master object, which would reside in the heap. And here a master object is a special object that the heap itself is aware of. Its role is to act as a gateway to the actual contents of interest stored in the heap. On the source side, our client code would have to ensure that the relocatable type requirements are observed by all the heap's contents. And of course, we would need to allocate everything that we want to be persistent from the heap, and at some point we need to serialize the heap. On the destination side, our client code would need to do the converse. It would need to deserialize the heap and obtain access to the heap's contents through the master object. So when I think about this problem, I see 6 not quite orthogonal concepts that I group into two broad categories. As I mentioned earlier, I call them concepts, but it's perfectly reasonable to think of them as being policy types. The first broad category I call structural management. And here the 4 associated concepts are the addressing model, the storage model, the pointer interface, and the allocation strategy. The second broad category I call concurrency management, and the 2 associated concepts are thread safety and transaction safety. And we're going to go into a little detail regarding these concepts in the next few slides. So let's start with the addressing model, the first structural concept. The addressing model is a type that implements primitive addressing operations. Its purpose is to provide access to raw memory segments, and I'll define what a segment is in a couple of minutes. In a way, it's analogous to a void star. It must also be convertible to a void star. The conversion is important because when we want to cast an addressing model object to a non-void pointer, we first have to turn it into a void star. Internally, the addressing model defines the bits or the pattern of bits that are used to represent an address. It defines how an address is computed from that pattern of bits. And this implies how the addressing model expects memory to be arranged. Now, from this description, we can see that the simplest example of a storage model is, in fact, a void pointer. There are really sort of 2 possible representations, right? The first is as an ordinary void pointer. I also call them natural pointers. The other is a synthetic void pointer or some other user-defined type. These kinds of pointers are also known as fancy pointers. The standard refers to them as pointer-like types. Next up is the storage model. And this is a policy type whose job is to manage segments. It interacts with an external source of memory to borrow segments from the operating system and return them to the operating system at some point in time. It provides an interface to segments in terms of the addressing model to the allocation strategy. And it forms the lowest level allocation in the stack. So what's a segment? I call a segment a region of memory that's been provided to the storage model by some primitive external source. And here I've listed some of those sources, both for Windows and for Unix-like operating systems, both sources that provide memory to the private address space and sources that can provide shared memory. Now, I use the term segment because other allocators call them blocks or super blocks, and I prefer to use terms without the word block in them just to avoid confusion. The next structural concept is the pointer interface. And this is a policy type that wraps the addressing model so that it can emulate a pointer to data. It's analogous to a T-star, for example. It provides enough pointer syntax to get the job done, whatever the job may be. It's convertible in the right direction to ordinary pointers, and it's convertible in the right direction to other pointer interface types. By in the right direction, I mean things like adding CV qualifiers, casting from derived to base, or casting from T-star to void star. Now, there are, again, two possible representations, a natural or ordinary pointer T-star or a synthetic pointer. And you may be wondering, well, what's the difference between a synthetic pointer and a random access iterator? Because they're actually very close. And the difference is conversion operations. I want to be able to take my pointer interface and apply ordinary casting operations to get ordinary pointers so that I don't have to go through convoluted syntax like I would with a random access iterator to get an actual address to something. And just as with the addressing model, the simplest example of a pointer interface to objects of type T is a T-star. Next up is the allocation strategy. And this is what we normally think of as an allocator. It's a policy type that manages the process of allocating memory for segments. It requests segment allocation and deallocation from the storage model, and recall that the storage model is a proxy for the operating system. It interacts with segments in terms of the addressing model. It divides those segments into chunks for use by the client, and it provides those chunks to the client in terms of the pointer interface. And also, by the way, a chunk is a smaller region of memory that's carved out of a segment to be used by an allocator's client. The final two concepts under concurrency management are thread safety and transaction safety. Of course, thread safety means ensuring that your program operates correctly in the presence of multiple threads or processes. In other words, no data races. And I think of transaction safety as meaning allocating and deallocating chunks in such a way that your allocator could be used by something that needs ACID semantics, like a database. This means providing operations like commit and rollback for your allocate and deallocate functions. Now, when I think about a relocatable heaps implementation, the structural concepts sort of build upon each other in a linear fashion. However, the concurrency concepts might be involved or intermingled with any or all of the structural concepts. And I'm not going to say anything more about thread safety or transaction safety other than to mention that thinking about them is a very important consideration in the design of your allocator, and you've got your work cut out for you. So how would we characterize stood allocator by this mental framework? It's pretty straightforward. The addressing model is void star. The storage model is implemented behind the scenes by global operator new using the operating system's memory management primitives. The pointer interface is T star, and the allocation strategy is also implemented behind the scenes by global operator new using whatever allocation algorithms the library writers have chosen. Likewise, thread safety is implemented by global operator new, and it is whatever your implementation says it is. Finally, as far as transaction safety goes, there is none. And these are all exactly what you would expect. It's worth noting that from the perspective of this talk, the major differences among common allocators is in the way they implement the storage model, allocation strategy, and thread safety concepts in order to improve performance, or at least in the way that they desire to improve performance. So, Recall that I want my relocatable heap to hold standard container and standard string objects, and I want to be able to operate on those objects with standard algorithms. The C++98 and 03 standards did not allow me to do this. Here's a load of verbiage from the 03 standard. The highlighted text in the first section shows how containers were free to assume that the pointer and const pointer type defs nested in std allocator are t star and const t star. As far as I know, until 2 or 3 or 4 years ago, all of the implementations did this, which effectively prevented standard containers from being used with allocators that allocate memory in terms of synthetic pointers. The second paragraph is an attempt by the committee to encourage library implementers to support more sophisticated allocators, but I don't think any of them really did. Here's a little diagram which sort of represents the old standards view of a container and its allocator. Containers would obtain their allocation services and part of their view of memory from the allocator template argument. And part of that view of memory includes things like the reference or const reference type defs, as well as the size type and difference type defs. But containers were totally free to assume, and most of them did, that a pointer was a t star and a const pointer was a const t star. Fortunately for us, this changed in C++11. C++11 and beyond, those offensive paragraphs from section 20 were deleted. And scattered throughout the library portion of the standard, many new requirements were added to support the idea of allocator-aware containers. I've listed 5 of these requirements here, the 5 key requirements which I believe, when taken together, indicate that containers must support allocators that employ synthetic pointers. I've listed some of the section numbers on the right, and these section numbers are from the 14 standard. Some of the numbers are slightly different in the 11 standard, and some of them are different in the 17 draft standard. So here's a picture of the new way, the new order. Working from the bottom up, containers must now obtain all information about memory from the allocator traits template. In turn, the allocator traits template obtains information about memory allocation services from the allocator and also from the pointer traits template. The pointer traits template has a very specialized job. It obtains information about the representation of pointers from the allocator. So, given the services provided by the allocator and the representation of a pointer provided by pointer traits, allocator traits collates this information and provides it to the allocator-aware container so that the allocator-aware container can go upon its merry way and do important stuff. Okay, so let's look at some example code. Here is one possible memory layout for a relocatable heap. We have a set of n segments, all of which are pointed to by what I call a backbone array of pointers. Constructing the address of something that lives in one of these segments is very much along the lines of doing a two-dimensional array lookup. It is exactly along the lines of a two-dimensional array from the old numerical recipes in C, if anybody used that early in their career. And by the way, the type of the backbone is an array of pointers to, well, unsigned 8-bit integers, but bytes. So one way of implementing this arrangement is in the process's own address space, perhaps by calling global new or some other primitive memory allocation service to allocate the backbone and the segments. And here I've got a variable called BP, which is the backbone pointer that points to the backbone. In the case of a heap that's based on shared memory, there could also be an administrative segment that contains things like shared memory segment IDs in System 5 shared memory, or segment names if you're using POSIX shared memory. Now, here I've tried to make the distinction between memory that's shared and memory that's private, even though shared memory gets mapped into the process's private address space. The backbone exists in private address space, and a call to shmat or mmap maps the shared segments into the process's private space. The backbone needs to be in the process's private address space because the mapped addresses for the shared segments can be different in every process that would want to use these segments. Okay, so let's look at some code. And I'm going to walk through some types, looking at basically some class definitions and one or two function definitions, and then moving on to a short demo which hopefully will work. So let's look at an example of the lowest level, the addressing model type. Now, I will say before starting that there are many ways that one could implement these concepts and make the system work. I've chose to implement the 4 structural concepts as 4 distinct types. If you decide to use this methodology, you could do it differently, and there's nothing wrong with that. In this case, my addressing model type is a class template, and it's parameterized on the type of the storage manager that will use it. I could have a private address storage manager, I could have a shared memory storage manager, I could have a stack-based array storage manager. And I would like to be able to use the same addressing model with all of those things, so I made it a template. Now we're looking at the prologue part of the class with important nested type aliases and the canonical member functions. And really all we need to know at this point is size type and difference type. And all of the canonical member functions are all defaulted, and here I've also made them no except to make them to optimize performance. The only ones that are not defaulted are the ones which take a parameter of null pointer type. Here's the middle of that class. I've got the first 3 functions, address, offset, and segment, which provide information about memory. And here the key function, the most interesting one, I call address. There are some helper functions which are used to perform comparison. And here there's a helper function to test for equality and helper functions to test for less than or greater than operations, but I've not shown them here for brevity. There's also some operations to allow assignment from a void pointer, and also to increment or decrement what the addressing model refers to. And this is a little bit of a fudge because in this case the addressing model is not truly acting like a void pointer because I'm allowing it to be incremented and decremented. It's actually acting a little more like a char star. But this little cheat makes things easier to implement downstream. At the bottom of the type, in the private section, I've decided to make the storage model a friend, and the reason will become clear. And I also have, and actually it's because it needs to call the constructor that you see on the next line, which is to construct an instance given a segment ID and an offset into a segment. And the next part, I've defined a bit mask, and I've defined a structure I call adder bits, which is a 64-bit structure. And I've duplicated it here to show the very bottom of the class. So the actual bits are stored in an anonymous union of a 64-bit integer and an adder bit structure. And the idea here is that the upper 16 bits, which are called M segment, will represent the segment ID, and the lower 48 bits will represent the offset into a segment, which means I'm going to have to do a little bit of bit twiddling to compute an address. And this is good old segment offset addressing, if any of you are old enough to remember this. So our example storage model is actually a very straightforward class. There are no templates here. It provides important interface information downstream to the allocation strategy type, which I'll also call a heap. Now, 2 items of particular interest here are the type alias, which describes the addressing model, so there's a little bit of CRTP here, although not really, and a static member function that returns an addressing model object given a segment ID and an offset. In the bottom part of the storage model, well, you see in the public portion there are some other helper functions, but the interesting stuff is in the private section. Here I've implemented a reciprocal friendship relationship with the addressing model. And I've defined some arrays of data which are segment. The first one, which is highlighted in black, is the backbone. It's that array of byte pointers which will point to the segments. The next is an array of addressing model types, which are the actual pointers that will be used publicly. And there's an array of size types which tell me how long each segment is. And there's this funny thing called the shadow backbone. And the purpose of this I will reveal later, and hopefully it will work correctly in the demo. So how are the addressing model and the storage model tied together? So at the top of this, the code in blue represents some snippets from the addressing model and the storage model. The first part above the ellipsis is from the addressing model, and below the ellipsis is from the storage model. And I've provided this here so you can understand how the addressing model computes an address. And this is the function in black at the bottom. And I've actually bolded the computation. As you can see, it's a pretty simple operation. The first thing that occurs, assuming, I will say it's the first thing that occurs, but of course it could be evaluated in any order. We dereference the segment backbone using the segment ID to get a pointer to a segment. We then apply the mask to the offset. We apply the mask to the matter bits to obtain the offset. And finally, we add the two together to compute a byte address or char star address. And that gets returned to the caller as a void star. Pretty straightforward. Okay. The third important type, and probably the most complex type, at least in terms of interface, is the pointer interface type. And most of that complexity in the interface comes from a desire to mimic ordinary pointers. We cannot do a perfect job of that, but we can get reasonably close enough to implement containers. And I've sort of provided an outline here of the various sections that we'll touch on. Canonical member functions, other constructors, other assignment operators, conversion operators, dereferencing and pointer arithmetic, helpers to support library requirements, helpers to support comparison operators, and finally, our data member. But in order to get there, and to help us provide desirable conversions in the right direction, we're going to turn to some custom traits types to do SFINE. And SFINE is a technique that allows us to remove a member function from overload resolution so that we can control the set of possible overloads that participate in that process. So the first template here is called Implicitly Convertible. And I use it to enable member functions when an implicit conversion from star to star makes sense. And these are the conversions I mentioned earlier. Adding CV qualifiers, going from derived to base, or from anything to void. And it just relies on std enable if, and std is convertible. The second is the logical converse of the first, and I call it explicit conversion required. The name is, when used in the code, the name is intended to convey that the member function associated with this SFINE must be used with an explicit conversion operator. And finally, the third trait I call implicitly comparable. And its job is to help with the help in performing conversions between synthetic pointer types and ordinary pointer types. We want to make sure that we're performing a comparison that makes sense, like comparing a base star to a derived star, or anything that adds CV qualifiers. We don't want to do things like compare a double star to a char star. Okay, at the top of the template is the prologue. There's a rebinder and some nested type aliases for consumption by standard pointer traits. I've also thrown in a random access iterator tag so that the synthetic pointer can be used as a random access iterator with the standard algorithms. There are no surprises in the canonical member functions. Everything is defaulted, and I've sort of cheated a little bit and made them no except, even though strictly they shouldn't be. Next are some custom constructors. The first two, grouped together there, allow implicit conversion from an addressing model object and also from a null pointer. The second two permit implicit conversion from compatible ordinary and synthetic pointer types. So if a U star can be implicitly converted to a T star, then these two constructors will participate in overload resolution. Otherwise, SFINE kicks them out, and it's as if they don't exist. And as an aside, I was pleased to see that this technique which I'm using is identical to the technique that Stefan Lavawade described as SFINE technique number 5 in his talk Tuesday. So I must be doing something partially right. Similarly with assignment, I want to allow assignment from a null pointer and compatible assignment from an ordinary or synthetic pointer. Again, compatible being adding CV qualifiers, derived to base, or anything to void. As with the constructors on the previous slide, if a U star can be implicitly converted to a T star, then these two assignment operators, the second two assignment operators, will participate in overload resolution. Otherwise, they're right out. The conversion operators I find to be interesting. The first provides an explicit conversion to bool, which is usually explicit, except when it exists in a context where so-called contextual conversion can occur. And the way to think about this is the conversion to bool will be implicit if it occurs inside of an if statement or a while statement or a for statement. The second conversion operator provides for an implicit conversion to a compatible ordinary pointer type. The corresponding implicit conversion to a compatible synthetic pointer type is handled by the conversion constructor that was a couple slides back. The third and fourth conversion operators provide for explicit conversion in the other direction. And here, I'm thinking of things like removing CV qualifiers, or casting from base to derived, or casting from void to something else. So when taken together, the upshot is that if a conversion can be done implicitly between a U star and a T star, then one set of member functions will participate in overload resolution and allow that to occur implicitly. Otherwise, a different set of member functions participate in overload resolution, and explicit conversion, explicit cast is required. Of course, a synthetic pointer needs to support dereferencing, indexing, and pointer arithmetic operations. And if this looks familiar, it should. It's identical to the interface that a random access iterator must provide. At the top is the pointer2 member function, which is provided to be used by standard pointer traits. And what this does is it takes a reference to some element and returns a synthetic pointer. Now, just like with the example addressing model we saw a few slides back, there are some helper functions here which I've defined to be used by the binary comparison operators, which I'm not going to show because they're fairly straightforward. And in these helper functions, equals, less than, and greater than, is where the implicitly comparable type trait is used to ensure that we're only going to perform comparisons that make sense. And finally, the private section of the class is quite simple. This is where an instance of the addressing model is stored. Now, there's a friendship declaration to all of its cousins. It grants friendship to any other synthetic pointer template, although its purpose is to permit the conversion, permit one of the conversion constructors we saw earlier, which means converting synthetic pointer of t, am to synthetic pointer of u, am. Assuming that conversion makes sense. So here's the allocation strategy. Another very simple class, but here it's a class template. And here I call it segmented test heap. It provides some type aliases which will be consumed by an allocator wrapper we'll see in the next slide. It provides pointer rebinding so that given any type t, it can provide a synthetic pointer for that type t using the addressing model, and it has very simple service functions, much like an allocator. Max size, allocate, deallocate, and the mysterious swap buffers member function. Now, note that allocate returns a void pointer, and note just above that void pointer here is a synthetic pointer representing a void pointer, but using our addressing model template argument. And here's an allocator wrapper, a simple class template that's parameterized by an element type and by an allocation strategy type, the thing we just saw. Its interface is compatible with stood allocator traits. The top is all very standard stuff. You'll see this in just about every standard conforming allocator. The basic type aliases that define what memory is. And also, there's the rebinder, which has been part of stood allocator, I think, since C++98. And this allows conversion from one allocator type to another by simply changing the element type. The bottom half here is also pretty straightforward. The allocate and deallocate member functions simply wrap the corresponding member functions in the allocation strategy. and they return or take synthetic pointers to do their work. The final two member functions, construct and destroy, these are part of the standard allocator interface now, and what they do is they perform in-place construction of an object given some arguments and given a chunk of memory, and also perform in-place destruction given a pointer to an object of that type. And for purposes of exposition, I've decided to include an instance of my allocation strategy type, which I'm calling mHeap. All right, so let's look at an example. What would this look like in practice? So I've tried to put together a fairly simple test function. Hopefully it will all make sense. I'll begin by including some standard headers. I'm then going to include some headers which define the types that you just saw. And I'm going to slightly break a rule here, and I'm going to import everything from namespace std. And I'm going to start defining some type aliases to make things easier. The first I'm going to do is I'm going to make a type def of our storage model, because these names can get very long. So what I'm doing is I'm calling my test heap the instance of our segmented test heap template, which is parameterized in terms of our segmented private storage model. I'm going to define our test, I'm going to bind the heap argument of our allocator type and only allow the element type to vary with this parameterized alias. Likewise, I'm going to define a test string by binding the character traits and the allocator type, but allowing the allocator type, but allowing the character type of the string to vary. I'm going to define a test list, and I'm going to bind the allocator type, but allow the element type to vary. And finally, I'm going to define a test map. This map will associate a string with a list of strings. And here, I'm going to bind the comparator and the allocator, but allow the key and value types to vary. So here's an actual function. The highlighted code shows the actual type that I'm going to allocate, and I call it demo map. So a demo map is a test map which is instantiated using a test string of char as the key type and a test list of test string of char as the value type. And this is where I'm going to allocate it. Now, the allocate function here is a simple helper function which is off screen, and I'm not going to show it here. But what it does is it allocates an object of type demo map using the test heap allocation strategy. I'm also going to allocate a work buffer for my key strings. Here I'm just going to implement a test string, and I'm going to use that as a buffer. Likewise, I'm going to allocate a string to be used as a work buffer for my value strings that will go in the list. And the top of the code here is a very simple nested loop that will populate the map. I'm going to create 10 elements. With different strings for each element, and for each element there will be each key there will be a value that's a list, and I'm going to put 5 elements in the list, 5 strings, each of which will have a different value. And here's the particular line of code that does that. Shouldn't be any surprises here. The only slight wrinkle is instead of using references, I'm dereferencing these synthetic pointers for each of those operations. Next, I'm going to have a loop that prints the contents of the map. Then I'm going to call this magic function swap buffers. And what swap buffers does, as will now be revealed, is it's going to take the data stored in the primary segments in the backbone, it's going to mcopy them into the corresponding shadow segment, and then it's going to swap the segments. In effect, I am relocating my heap. Finally, I'm going to print the contents again. So recall, this is the picture of our memory layout. And this shows our primary backbone and primary segments, and our shadow backbone and shadow segments. And as I said, swap buffers will mcopy data from the primary segments to the shadow segments. It will then swap the pointers in the backbone arrays, and we will effectively relocate the data. Okay, and so now with your indulgence, I'm going to try and do a demo here. Give me a moment. Okay, here I am in a CentOS 7.2 virtual machine, and I've actually queued up GDB with this program, and I've got some breakpoints set. And I am redirecting output to cout to the terminal that you see on the right, and hopefully this will be readable. So I'm going to start the program. So here I am at the top of that function. So I'm going to allocate the map, I'm going to allocate the string, and I'm going to step into my loop that does the population. And I'm going to do this a few times because it's amusing. Okay, so I've just done the first element. And I'm going to continue to the next breakpoint. And you can see on the right is the output from that operation. So for example, for the 10th element, the key string was, this is test key string 9, and the elements put into that list were the strings that end with 901, 902, 903, 904, and 905, right? So I've been able to allocate memory. I've been able to use a standard string, a standard list, and a standard map, which exist inside this relocatable data buffer. Now I'm in the swap buffers member function, which is part of my storage model. And I'm just going to step through a couple iterations, but you can see here is where I'm taking data from the primary segment and I'm copying it, doing a binary copy into the shadow segment, and then I'm swapping the pointers between the two backbones. And this will go a few times. And on the right, you can see that I've printed out the same data. After the swapping, I've printed out exactly the same data. So what I've done, in effect, is I've taken a heap, I've made a binary copy and relocated it to a different address inside the same process. And I've been able to preserve the class invariance and make things like strings, lists, and maps work. So if I can do this, I can also serialize the heap by copying those bytes, the bytes for each segment, to a file, and at some point in the future, duplicating the layout of memory with the backbone and the segments, and loading those bytes back into the segments, effectively providing a relocatable heap. All right, so that's it for the demo. Okay, good. All right, so concluding comments. Possible applications. Well, in my case, these are the three things that I'm interested in. And of course, I don't have much imagination, so I'm sure you can probably think of other ways that this could be used. I'm interested in using this as a heap for allocating memory from my shared memory databases, or actually for my databases, and having them exist either in private address space or in shared memory. I think these could also be useful if one wanted to implement a very highly instrumented debug allocator. I mean, think about being able to capture information from the pointer interface and capture information for every single operation that a pointer does, whether it's being incremented or dereferenced or indexed. With the pointer interface, you can capture that information. You could capture stack information for every operation, whether it's the pointer interface or in the allocation strategy or in the storage model or in the addressing model. As I said before, This is simply one possible implementation of these concepts, and there are many ways that this could be done. In early work, I actually made the addressing model be a type that is nested within the storage model. And that sort of made the reciprocal friendship a little bit easier. I'm not sure that's the best way to do it, but it's worth a try. Finally, this is a work in progress. And I will say that I've tested this. I've done some light testing with Clang and Visual C++. And Clang and libc++ is pretty good at its allocator-aware containers. So far, all of my tests pass. With Visual C++, 2015, Update 3, all of the tests pass except for one. And that has to do with std_map. So other than that, I think this is the end. Are there any questions? Sir.
When you implemented your allocator interface and you defined all your types in the allocator, is there any advantage or disadvantage to doing that versus specializing allocator traits yourself?
I actually wanted to do this in such a way that I did not need to specialize allocator traits. I wanted to provide an interface to allocator traits which was close enough to what std_allocator provides so that that was not an issue. But I don't see any performance benefit one way or the other. It was an implementation decision driven by laziness. Sir.
How do you deal with binary compatibility, revision of your data objects, things like that?
So the question is, how do I deal with binary compatibility? Well, I don't deal with it per se, other than to say, as I said in an earlier slide, that there are requirements for the types that need to be relocated, and there are assumptions that are made when you do the serialization between the source and destination platforms. And those assumptions are that the platforms on the source and destination side are basically the same, that the class member layouts of objects on the source and destination sides are exactly the same, and then I'm using the same object code on each side. Effectively, I'm using Clang 381 on the source side and Clang 381 on the destination side with the same compilation settings. Sir?
What are the performance implications of using specialized pointers?
Well, performance is going to be slower. And in this particular case, instead of dereferencing a pointer, there's an indexing operation, there's a bit masking operation, and there's an addition operation, and then finally, when that's done, a dereferencing operation that must be done, right? So the speed of the dereferencing itself is naturally going to be slower. My experience, depending on the application, is that in a lot of circumstances, that performance decrease sort of gets buried in all the other costs. And if one is designing if one were to design a container which used this scheme, if I were going to create a new kind of container that used this allocator or this scheme, what I would do is once I got a pointer back from the allocator and had constructed the object, from that point forward, I would actually only use the ordinary pointer. I would use the synthetic pointers basically only to carry information for allocation and deallocation operations. Once I had them, I would convert them to ordinary pointers and use them that way. Except, of course, where you need to store the synthetic pointer. Think about an element in a doubly linked list, right? For this to work, each of the two pointers in the node of a doubly linked list needs to be a synthetic pointer. But if I need to do operations on that node, I might convert one of those pointers to an ordinary pointer and do it that way. So I guess the answer is, I don't have a good answer for you, and it depends.
Well, so just to expand on that, have you tried to run this test like the standard allocators and with specialized allocators?
So the question is, have I tried to run this test comparing the performance of the same containers, the same element types with the standard container and with this demo? And the answer to that is not yet. I do expect a decrease in performance, but I've not measured it. Sir?
Can you describe your deallocation implementation and its effect on fragmentation in your allocator?
Yes. The question is, can I describe my deallocation implementation and its effect? And I will tell you right now that the allocation and deallocation strategy that I used for this demonstration is very simple. I have an array of bytes, and I allocate from the bottom, and deallocation is a no-op. I call it the leaky allocator. I don't really care about allocation correctness at this point. I'm trying to make the allocator-aware containers work, to make sure that compilation and linking can occur and everything works correctly. Now, the idea behind the allocation strategy, which I think is what you're really getting to, is that's the piece of the puzzle that would allow you to implement allocation and deallocation algorithms to improve performance the way you want to do that improvement, whether it has to do with locking and unlocking, or the way that you divide memory into chunks or deallocate them to minimize fragmentation. That's the role of the allocation strategy, and it's up to the implementer of that to make that work the way you want to. I chose something very simple because I actually wanted to make this work first. Okay, well, I'm told that this is the end of the hour. Thank you very much for coming. I greatly appreciate your time and attention.